All right, before everybody evacuates the room, let's start. We have until 3:45. Should ask questions at the general for all three speakers. Let's start. Any? Okay, we have one there.
Yes, I had a question for Diane Lambert. I think it was raised by the question that the moderator asked on this. I mean, you've assumed independent samples in your n-gram, I guess. Is that right? I mean, when you look at the larger and larger volumes of samples, this is in your language model. And the question is, what's the effect when they're not independent samples?
I'm sorry, I didn't quite catch the question.
Okay. You're talking about your translations?
Yes.
And it was pointed out that some of the translations that you're mapping against are probably computer-generated translations. Mm-hmm. And I assume the assumption underlying your model is that the samples you're looking at are independent samples.
Yes.
And so if you start with only 5 real samples and through your modeling you've generated 5 million samples, you then don't have 5,000,005 independent samples. You really only have 5 of them. So what's the effect on your outcome? What's the effect on your model if in fact these are not independent samples as you go to large sample sizes up to the 215 billion samples?
So that's a good point, but I guess there's probably some dependence in there, but there's enough independence left that you clearly get a big boost up from putting the additional data in. But you're probably right that we would get an even bigger boost if if all those samples were independent.
My question sort of has some relation to the topic of the last speaker, but I mean it's a question for everybody in this panel, or perhaps in the panel that talked in the morning. So Ryan described to us essentially some programs that create other programs to solve problems, to look at data, as machines creating other machines to look at data. And from what I see around us, data are becoming the amounts of data are so huge, so overwhelming, that I feel that we're reaching the point that we as humans cannot have any real useful understanding of the data. And even though we may have useful visualizations as those that were described, those in the end may not help us solve difficult problems. We may be, by chance and error, build very intelligent machines that we may be able to judge their judgments as correct and be able to verify them, but not much more. Do you have any thoughts on if we're reaching that stage, or if we can do something to perhaps? I
mean, I think that the field of statistics is about coming up with concise explanations of the data precisely. And it's not obvious to me that sheer quantity of data has a negative effect on that. I think the contrary, it actually has a very positive effect on that because of sample complexities and so on. And I should also say that I mean, Cynthia, a big chunk of Cynthia's talk was about interpretability specifically, about observing that it's possible to build great models that are just about being able to understand them. Not to put words in Cynthia's mouth, but this is that was the thing. Yeah.
I don't think huge amounts of data is going to undermine the knowledge discovery process. I think the knowledge discovery process, as it was invented originally, maybe 30 years ago, is still in place, and I don't think any hugeness of data is going to take that away.
But on the other hand, I don't think that hugeness of data necessarily saves you. So if you don't know where the data came from and you don't know how it was collected, and you don't know what contributed to it, then the fact that there's a lot of it is not any better than having just a small amount of it.
Yeah, I guess, we should be collecting data to inform particular kinds of questions and decisions, and just sort of storing all of our server logs or whatever is not, I think, is not the same as collecting data. It's just sort of, I don't know, maybe that's an example of creating a data tomb. Is that what a data tomb is?
So a data tomb, I think it's data that's been repurposed. It's data that's been collected for one purpose and then used for another purpose. Yeah. So it's data that normally would not go used. The data tomb, a place where you put data and never look at it.
One question.
So I have a question about model interpretability. So often you would, when we do a regression type of problem or tree type of models, we could end up with a lot of different models which have similar predictive power. And you pick one of them, you would have one interpretation. You pick another one, it would have a different interpretation. Sometimes can be the opposite direction. How would you handle this kind of situation?
Okay, so that's a really good question, and so I think let me start by just repeating the question a little bit. So there are many predictive models for a particular problem that predict approximately equally well, and so which one do you pick? So if your goal is prediction, it doesn't matter, right? Because they all predict approximately equally well. They're all good. You might have another goal in mind. So for instance, I'm really interested in interpretability. So among this class of equally good predictive models, I care about the ones that are the most interpretable. And I say the ones because there isn't just one. There could be many, and they could be equally interpretable. Right.
They may have different meanings.
Exactly. Well, you have to find another objective, because if your objective is predictionability and you have a class of equally good models, you need another objective to choose between them. Either is it interpretability, is it decision-making ability, is it, whatever the second objective is, that'll help you determine among this class which models you actually want.
What if they're equally predictive and equally interpretable?
Find another objective then. I mean,
Flip. You can always flip a coin, right? Okay. Natasha. Oh, okay, sorry.
This is a question for both Ryan and Diane. Do you see perhaps a tension between the interpretability objective of Diane and the capability of bringing the human out of the loop, in the sense that, for instance, when you take the human out of the loop, you get the capability of running more complex models, perhaps with 13 parameters, as you were saying, and not actually understanding why you chose the parameters you chose, but the algorithm did it for you. So you don't even have one expert postdoc in Google knowing why the parameters are what they are. So is there a tension, or is there, and if there is a tension, is it just a matter of deciding on what your objective is, if it's interpretability or large-scale applicability? Or can you talk about this?
Sure. I mean, I think that the kind of things that I'm talking about are almost entirely about about prediction. The objective function that we frame via cross-validation is about generalization performance, full stop. And these kind of high-level hyperparameters, there may be sort of, like you say, sort of 30 of them, but really the number of parameters in one of these things is sort of millions, like one of these, like a convolutional net has many, many, many parameters. And frankly, for those kinds of things, interpretability is pretty far down the list of desiderata. But I don't know, I guess Cynthia has done a great job of articulating some like criteria for, like kind of objective criteria for interpretability, though, and sort of thinking about the compactness, for example, of decision trees. And you could imagine trying, or not decision trees, but decision lists. And and you could imagine trying to apply this same kind of automated methods to find compact but predictive representations.
Yeah, I mean, sparsity, for instance, has been around for a really long time as a measure of interpretability.
I might just throw out that there's been an interesting effect, which is that in the network, the neural network specifically, when they've found very good values for the different parameters, those have often quite surprised the experts and been different from the intuition that they had built about these things. So they're not interpretable for everyone, but they're often quite interesting for the experts themselves in that they contradict kind of conventional wisdoms that had been built up over some of these labs over time about the right way to set these things up.
All right. Rahul?
So two small questions. The first one actually builds on that previous question asking about sparsity. Typically, you might be using a cost function, which is a modulus function of your error or something of that sort. So you lose differentiability. How do you deal with that? You lose twice differentiability. How do you deal with that? That's question one. Question two was, you alluded to this a little bit in your talk, Ryan, but this is the notion of how do you actually build noise into these kind of models? Do you just add additional parameters, or what's the canonical mechanism?
I'm afraid I don't understand the question. What do you mean, how do you build in noise? I mean, there's noise in the data. We don't build in noise.
Well, typically, if you're doing measurements, like if you're a physicist and you're doing measurements, there's going to be error bars on your stuff, which may or may not be modelable by a particular. You might say all the errors are Gaussian, but they may not be Gaussian.
Oh, I see. So you're asking about an approximation error question?
Yeah, it's kind of like an approximation error because you don't really have. I mean, you don't have additional samples. You just have a certain error model for each point in your data set. That's the question.
Okay, so is the question, how do you choose the function class that you work with for a particular data set? Like, how do you use the class of, what class of models is that the question?
The question is a bit more general. It's how do you just deal with a situation where you may not have easily modelable errors on in your data set?
Sorry, I'm sorry.
I think it's related to the question Fernando asked before. If you don't know if the error is Gaussian, how do you go from there? Is that right, Rahul?
Yeah, if you don't know the error on each data point is Gaussian, it may be coming from you don't have necessarily a simple process to describe your errors. If it was Gaussian, I'll just add an additional parameter to the model and I'll be done.
Yeah.
But if it's not, I mean, I was just wondering if you guys have had experience doing this and what do you do?
Yeah, so as far as I know, there's no really good answer to that question in existence, and I don't think there can be because of the no free lunch theorems. I think a lot of the visualization that you do can help you understand the data well enough that you can choose the right class of functions for your data. You want to choose something that's simple, right, relatively simple, but has the complexity just to model your data well and no more. You guys can
I guess I would add to that by saying, I mean, there's a kind of a large industry associated with modeling, say, doing regression models with non-Gaussian observations, logistic regression and ordinal regression and all these different things. So certainly people spend a lot of time thinking about different kinds of likelihoods that might exist on the data. If we're sort of trying to operate in the sort of mythical assumption-free regime, then I don't think there's much hope. But if we are willing to kind of make assumptions and make models and then check them in interesting ways, then we do have a pretty large toolkit that's been developed since sort of Fisher and friends. So I guess that doesn't. It's a hard problem to be sure, but it's something that people have been working on and I think made interesting progress on over many decades. The actual statistician maybe has something to say.
I mean, I think the question you raise actually goes back to what Ryan is talking about, which is it really possible to take the human out of the learning problem if you have to know something about your outcome. So it depends on which human I think you're taking out, right? Are you taking out a human who has some understanding of the data, or just a human who has a problem and grabs a data set and will, just not understand that the assumption that the data have some Gaussian form is built into it.
Good point.
So Ryan, seemed like the promise of your talk was that you could remove the human somewhat from the optimization step of the learning process. And it seems like then the human's role maybe moves back to specifying the objective function. And in Cynthia's talk talked about some interesting ways of posing objective functions to emphasize maybe interpretability or simplicity. It still seems like the ideal is even higher level than that, that the human has some sort of very high level goal that he wants to understand things or he wants some sort of benefit to society. Do you see ways of kind of automating even these higher level things, like specifying the objective function, so that you can start with even kind of like a higher level statement that's closer to, I don't know, some sort of vague thing that humans understand, and then from that, turn that into math and then optimize it? How far out of the loop can you take a human?
That's a great question. I think ultimately, the point is to produce something that is, that can be understood in some way. Maybe it's a black box that produces a label of an image as being a dog versus a cat, and we still kind of need the human to define these concepts and to define what it means, what the loss function is for getting that question wrong. So I think there's been interesting progress on kind of different parts of machine learning that we've talked about today in making it easy to specify statistical models of the world. So there have been these really interesting tools in probabilistic programming, for example, that allow you to talk about kind of graphical models, to model different kind of intuitive phenomena maybe, and without having to worry about the details of performing the inference later. But it's what you're describing in some sense is what we call AI complete, right? To have something that interprets what it is that you'd really like it to do and that does it automatically without having to think too hard. I think we're a long way away from realistically doing that, and it would look a lot like AI.
I think when you're working with domain experts, a lot of times they have an objective in their head, but they can't actually write it down. And when you have that situation, it's really hard to give them what they want because they don't really know what they want. So I think taking the human out of the loop in those kind of situations is going to be really difficult. So in that sense, I'm not sure that how close we are in that sense.
So I am very uncomfortable taking the scientists out of the loop. There's many discoveries that have been done by serendipitously looking at something. We just came back from Chile and we heard the story how the first supernova was discovered. They were just looking at some stars and all of a sudden this thing was 10 times brighter than it should be. Long story short, Nobel Prize. So I think trying to do everything and taking the human out is not the best idea. Maybe what we need is have the human as small as possible interaction, but not taking out totally. I'm not comfortable with that personally. Still want my job. So.
I mean, let me give you a small counterexample.
Yes.
That is from.
We are out of time, right?
Oh, are we?
No, go.
Okay, I'll tell you later.
No, go.
No, it's a hypothetical counterexample. It's basically that, so we've been working with these folks at Berkeley National Labs on interpreting the Sloan Digital Sky Survey. So trying to really build sort of 3D map of the entire universe based on these images. And it's very tempting to build in all the physics you know about stars and galaxies into this. And on one hand, that's really appealing because it lets us do better modeling and it's more interpretable in the language we all understand. On the other hand, that essentially eliminates the possibility of discovering something that we don't already understand, right? And so there we actually want to be quite flexible, and if we can take the human out of the loop, then those assumptions that are biasing us towards existing knowledge go away, right? And so maybe if we want to discover another kind of thing like a supernova in these data, then it would be necessary to relax the strong physical assumptions and let it be kind of non-parametric. So I think there is a tension here.
How can machine learning enable serendipity?
Yeah. Outlier detection, maybe? Yeah.
All right, I think it's a good point to stop. Proper comment. And we return back 4 o'clock.